Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge number 12. So the problem is a number of nodes in a subtree with the same label. So basically what we have is we get a tree, which is basically just a connected and directed graph that has no cycles. That's sort of the definition of a tree. And it has n edges, n nodes from 0 to n minus 1, and n minus 1 edges. And we have the root of the tree, which is has to be node 0. And each node has an additional data, which is the a label. So for example, node 0 has A, node 2 has A, node 1 has B, and you get the idea, right? And we get the edges array, which tell us that A is connected to B, right? But what we want to do is return an array answer where for each position it represents the number of nodes in the subtree of that node, such that they have the same label, right? So for example, let's pick an example here. Let's say so for this tree, position 0 needs to be the number of nodes in the subtrees at 0 that have the same label as 0, which is A. So of course we count the node itself, so this A, and if we look at the subtree, this one is not A, this one not A, but we have an A here, right? And that's the only one, so we have 2. So that's what we return for 0. For all the others, it's only 1 for each. For example, for B, there's only this B in this subtree here. Same thing for 4, there's only D because that's the only node. Here, there's only one A in this subtree, and each one of them has only 1, which is itself, right? So that's the idea, and that's why we have all ones here. If we take a look at this one here, node 0 has label B, and you can see itself, and then all of its children have B. So 3 for its children and itself 1, so 4 here, and that's why we have this one. And for the second one, which is 1, we have B here, so 1 for itself and then 1 for its child, so 2 here in this subtree. And then the other ones have just 1. So that's the idea here. Now, how do we solve it? This is actually a pretty similar solution to the to yesterday's problem, and so we can apply the same idea, which is use DFS. But let's see how it looks like. Okay, let's see how we can solve it. I modified the first example a little bit to make it more interesting, but the idea here is we can use DFS because the only information we need is to find something for the subtree of each node, right? Whenever you have that, where it's something for a node, what it cares about is data for its subtree, then you can of course use DFS because that's what DFS does. It goes to a subtree and bubbles up to you, right? Bubbles up to that node. And so that's exactly what we are going to do. And when we are using DFS, we need to think about what data does each subtree or child need to return to its parent, right? And so, for example, here, what do we need to return? Well, the parent needs to know that there is one A underneath it here on this side. And so we can return either a map or a counter that tells us the number of A's, right? Because this may be another subtree where it has another A, maybe it has another B, maybe it has another C. And so here, this one we need to return that it has one A, and if it has this subtree, it will need to say I have 2 A's, I have 1 B, and I have 1 C. So it will need to return either a map or a counter like this if it had a subtree, right? So that's why we need a map. It's not enough to just have tell it, for example, we have 2 A's, right? Because you may have more different labels underneath, right? So that's why we need some sort of a counter. So let's apply it though on this example. So what does it return to its parent? It returns that in this subtree starting at myself, there is just one A, right? And then what does this one tell it? It tells it that there is one B, okay? Now, what does a node that gets data from multiple children do? How do we add these two together? Well, what does B need to tell its parent? Well, it needs to tell it that this subtree has both one A, one B, and then it needs to add itself, so it needs to tell it that it has both one A and two B's, right? So we just need to concatenate the two, add the two counters together, and then add ourselves. And so here we need to tell it we have one A, and then we have two B's. Okay, and by telling, what do we mean a child needs to tell? Means basically that's what the child needs to return, right? And then with recursion, it will go back to the parent. Okay, so let's go back here to the second child. So what does this one needs to do? So it needs to tell it that there is one C, and this one needs to tell its parent that there is one D. And so this one needs to add them together and bubble them back up. So how does it do that? So it has still one C, one A from itself, and then one D. And now the parent can take a look. Okay, now what do I have? So the parent itself now has two A's, three A's actually, including itself. And it has two B's, right? It has one C, and then it has one D, right? But at the same time, remember what the problem needs us to return is a result or an answer array that tells us at each position for each node how many of its own labels. So, and since we have this occurrence data, we can just check, right? We can just, for example, here, once we construct this, we can say, once we construct for itself, we can just say, let's call this occurrence, right? We can just say occurrence of this label A. How many are there, and add those to res. So basically what we will do is we will say just answer of I is going to be equal to the occurrence of the label of this node. And what is the label of the node? It's just going to be, we have, by the way, the problem tells us the label in strings. So for example, it would be something like A, B, A, for 3C, for 4, it's going to be A, and then for 5B, and then D. So it will be something like this, with the indices being the nodes. Okay, and so here we can just say labels and get the index, which is the node, and from there take that label and then just get the occurrences and assign those to I. And we can just initialize this array to a list of zeros and zeros initially, and with this occurrence it will get filled up, right? So that's roughly the idea. The main one is each child returns to the parent the occurrences of the subtree rooted at that child, and then as we do that traversal, we'll fill this answer array, right? Okay, so that's pretty much it. Now let's code it up and make sure it passes test cases. Okay, so let's implement this. Now, one thing we need to do though is we get the list of edges as a list of A, B. So we'll do the same thing we usually do, which is create a map so that we have the key being a node and a value being the neighbors of a node, right? So something like this. So we just go through the edges, and since it's undirected, we'll say A is connected to B and B is connected to B when we have an edge A to B, right? And then what we need is to define our answer array that we will fill up. So it's just for, because we have 0 to n minus 1 nodes, we just will say we'll have n zeros, right? And then we'll of course do visited set because we are using DFS. And then we will start our DFS from the root, which is always 0. That's what the problem says, so we can just do that. And then at the end we want to return answer that we filled up in our DFS. Okay, so now we will define our DFS. So our DFS gets a node. Okay, sorry about that. Okay, so of course we will need to have a base case, and that's, let's just do it when a node is visited. We want to return empty, but this one returns a count, right? So let's go back to it, but we need to return an empty count. Yeah, because there is nothing underneath it, right? Because it's already visited, we don't want to recount it again. And so we can actually just return an empty count, which is just you could use a map, but or use a counter in Python, which is just a map that counts elements. And then we want to fill our visited node. And then now we want to define the counter for this subtree rooted at node. So this is basically counter count of labels for this subtree rooted at node, at the node that we are calling DFS function on. And then we'll go through the neighbors of that node and fill the counter, right? And so to do that, what we said in the overview is that the parent will collect the occurrences and add them together for its children. So if it has two children, let's say with A, then it will add them together and have A equal to 2 instead of A1, right? And so counter actually supports addition, which will exactly do that. So basically, if we had two counters from the children where one is 1A and the other one is 1A, then it will add it up to 2. If it was something like maybe one has 1A and then B1 and then we have a new one C1, then what we'll end up with is a counter that is like this. Okay, so it supports addition pretty well, and so we'll call it on DFS of the neighbor. And now what we want is we want to add the occurrence of the node itself, right? So we want to get the label, which is, as we said, it's just by getting it from the index, which is the node value. And then we want to count this occurrence, right? For example, let's say the node has B, and we had this, we want to increment B to B2 because this is the counter for subtree rooted at node, including node, right? And so here we want to increment it by 1, right? And then we want to fill the answer for this node, right? Because we visit each node only once, and so we want to fill the answer for it. What is the answer? Is the occurrence of label in this subtree rooted at this node, which is just occurrence of label, right? And then at the end, we want to return this occurrence map or counter, right? And that's pretty much it. That's the main idea. So we return this to the parent, and the parent does the same thing. And let's just clean this up a little bit. And that should be it. So let's run it. And let's submit. And that passes our test cases, right? Yeah, so that's pretty much it for today's problem. Please like and subscribe, and see you on the next one. Bye.